We have seen the dead neuron problem implied by ReLU function when the input is negative. There exist several modifications of the ReLU function to circumvent this issue. The first one is a leaky ReLU, which is displayed here. It is a variation around the original ReLU function, since the leaky ReLU outputs the maximum between alpha x and x, where alpha is set to 0.1. Note that setting alpha to 0 gives the original ReLU function. This new function has a constant slope for negative numbers, which allows the parameter training due to non-zero gradient. In deep learning, you can also use a very famous activation function called absolute value rectification, where you take alpha equal to -1. In mathematics, this function is called the absolute value. You can also learn the parameter alpha in the leaky ReLU, which you can do as you train your network. The parameter alpha thus becomes a trainable parameter of the neural network. Another variation around ReLU is the exponential linear unit, which, contrary to previous functions, is differentiable everywhere. So far, I did not comment on the fact that the ReLU function and its variance was not differentiable in 0. In practice, this is not a problem, because the input, i.e. the linear combination, is not likely to be exactly equal to 0. Even if it is the case, the gradient is set to a default value and the training goes on. Therefore, being non-differentiable at 0 is far less damaging for the training than being equal to 0 for all negative numbers. For each activation function, the corresponding paper that design it is mentioned. So you can take a look at these papers if you want to have numerical results or more precise ideas about how activation functions are designed. Another function is the maxout, which is simply a piecewise linear function whose precise expression is given by the maximum of k linear combinations of inputs, where k is a parameter you can specify. This function has no saturation problems, except if some slopes are equal to 0, which is unlikely because these parameters are trained with the other network parameters. Maxout function offers a lot of flexibility. It can approximate complicated functions, but the drawback is that the number of parameters is multiplied by k, where k is the number of pieces, i.e. the number of linear functions. One good point for maxout functions is that they resist to catastrophic forgetting. Catastrophic forgetting describes the fact that if you train an algorithm on a particular task, and if you train it to solve another task, then it will forget about the first task you learned. More specifically, if you train a classifier to recognize images of animals, and then you train it to recognize vehicles, it may happen that the resulting classifier is not able anymore to recognize images of animals. But of course, at the end, you want to end up with an algorithm which is able to recognize both animals and vehicles. Maxout is one of the functions that seems to be able to do this job. Here is the last activation function we will see. It is a swish function which was created in 2017. Swish interpolates between a linear function and a ReLU function. Its expression is given below, which is simply x times a sigmoid of parameter beta. Contrary to previous activation functions, this function is non-monotonic for some values of beta, which seems to be an important feature as shown in the original paper mentioned here. We have seen many activation functions, so a natural question is which one should we choose when implementing a neural network? First of all, there are no generic rules that work in any case, even if there are some trends in choosing activation functions. One thing that seems to be admitted by a vast majority of researchers and practitioners is that ReLU or swish functions work well in practice. You may want to test the variance around ReLU functions, particularly if classical techniques, like setting positive biases, does not allow you to get rid of dead neurons. If you are in a testing spree, you may try hyperbolic tangent, but in general do not expect too much from this function. The sigmoid function is not often used inside the network, since the saturation phenomenon is even stronger than the one observed for hyperbolic tangent. Also remember that the performance of your whole network depends on the activation function, but also on the number of hidden layers, the number of neurons per layer, and other features we are going to see.